So I think the key thing, we talk about the Deutsch algorithm. The Deutsch algorithm is the simplest algorithm that you can show quantum parallelism with, but it's not very useful. Okay, just two inputs and two outputs, but the key element of Deutsch algorithm is this part over here. So we talk about the Deutsch algorithm. It has this UF, and then you have X, and then you have Y. Yeah, other NOT gate, and then you have this coming in, and then you have a 0 bit coming in here, Q1, Q2, a 1 bit coming in here. Okay, and then there's this unitary transform, that transform it to X, and then another bit coming out. The key thing to this Deutsch algorithm is actually this part over here. Okay, this part over here, and it's further elaborated in this book. If you read this book by Nielsen in Quantum, it has a lot of examples. Lots of things on quantum information and quantum computation. So quantum information and quantum computation grows to be a pretty big field. Essentially after 1980, after Bell's theorem had been validated or so. Okay, so lots of people jump on the bandwagon and do all kinds of quantum algorithm, quantum communication, quantum things. And there have been quite a bit of money poured into this kind of thing as well. Okay, so the key thing about this is that if we have this part of the thing, okay, if X is 0, okay, if Q1 is 0 at this stage, Q2 is let me see. What I have here in this book is that at this stage, if you have this as an input, after you go to the Hadamard gate, you can have X be equal to this as an input, and then Y is in the 0 state. Okay, at this stage over here. And then you can implement this with a quantum computing system because U hat is unitary. Okay, U hat is unitary means that you can write it as a unitary transform of some sort like this. Okay, or maybe with an integral involved, if there's a time integration involved. But what happens is that if U is unitary, can be implemented as a time evolution of a quantum system. And what is great about this is that when the input is something like this, then the output that you have in the bottom here, in the bottom port here, is something of this form. Plus 1, f of 1 over root 2. Okay, so this is equal to y plus modular addition to addition fx is equal to that. The great thing about this is that when the input comes in like this, there's kind of a superposition of two states. You have both a 0 state and 1 state coming in, and what comes out of this port is actually also linear superposition of two states. Okay, and that you have two outputs, F0 and F1, with just one operation. That is, both F0 and F1 are available. Okay, and because they are available, you actually do not know what state you are in, but they are developing both of these states, and if you go through some operations with this thing, apparently you can decide whether this is a balanced F or a, I guess the balance F, there was a balance and a constant F. Okay, the balance, F is balanced, F is constant. Okay, F is balanced means F of 0 is not equal to F of 1. Okay, and f of 0, f of x, the output is either 0 or 1. X is also belonging to 0 or 1. Okay, the input x is also belonging to 0 or 1. When it's balanced, then this is thing, and then it turns out that if it is, this is balanced. This is constant. Constant means that f(x) is f(x). That means that f(0) is f(1), f(1) is f(0). That's what it means. That's what this notation is. Okay? So you can immediately determine whether you're in the balanced state or the constant state. So if you have a quantum system with lots of inputs, say if you have one input here, okay, another input here, and an input here, and this is psi 1 might be equal to C1 0 plus C2, or let me call it C0 0, and C1 1, and then this input to this port here is, let me call it C11. Let me find a better notation for it. C02, 0, C1, 2, 1, and then psi 3 is with C03, 0 plus C1, 3, 1. And the kind of thing of Ci or psi I is C0I, 0 plus C1I, 1. So it's always in a linear superposition of two. You have all these ports coming in, and if you can make all of these states coherent or quantum coherent, that's very important. You get all these states to be quantum coherent. Then you can design a quantum system to evolve all these states. You might write psi as psi 1 times psi 2 times psi 3, the product state of these quantum states. Psi n state. Okay, then you can get this state to evolve coherently with time. Okay, then you can change all these coefficients. You can change all these coefficients, which means that you can change all the qubits of all these quantum systems. Okay, and you can change them in parallel. And just imagine that you can change them in parallel. You can go through zillions of quantum states. Okay, you can go to zillions of quantum states, and you can have all these quantum states do work for you in parallel, not in series. That is the power of quantum computing, because if you expand this out, then this will be, if you multiply this with that, and with that, and so you get a linear superposition of zillions of quantum states. And then the quantum system can be in any of these states. We don't know which one until you do the measurement. That is the power of quantum computing. Okay. That is something I like to emphasize about quantum parallelism. And how do you get all these states to be quantum coherent? Well, there's something that is very interesting that you have learned in this course, which is the coherent state in electromagnetics. For instance, in NMR, you have lots of spins. You have lots of spins in the human body, or lots of spin in the sample. And you want to get all these spins to be quantum coherent. You can get them to precess, all these spins to precess at the same frequencies. And you can excite them with an RF field, RF-EM field. Okay? And if your RF-EM field is in the coherent state, okay, what is a coherent state in electromagnetics? You can think of coherent states as electromagnetic oscillations that are causing little dipoles all over space. And these little dipoles can come from electron-positron pairs. Okay? And these dipoles are oscillating coherently. They're not oscillating coherently only classically, but they're also coherent with respect to each other quantum mechanically. That's very important. Okay? Because these are quantum particles, and they are forced into oscillations. So if you can excite these spins with an RF EM field, which is the coherent state, you can get all these particles to be quantum coherent with respect to each other. And people have done this using RF field, and in optics, what people are trying to do is that you have a bunch of trapped ions. Okay, trapped ions. And trapped ions might have spins. Okay, they might have spins, and then you may get all the spins to precess or oscillate. And how do I get all these spins to be coherent with respect to each other? What they do is that they do with the light source. Okay, they excite those spins with the light source, and if this light source is a coherent light source, you can get all these trapped ions to be coherent with respect to each other. And it's the same as saying that I want all of this to be coherent with respect to each other. And when they get them to evolve, then they evolve as a coherent quantum state. Okay, that's something very important. And the coherent state of the light source is very important in getting all these trapped ions to actually oscillate coherently with respect to each other and produce a coherent quantum state. And then you can do quantum manipulation of these trapped ions to get into different quantum states and then have a quantum computing going on. Okay? Yes?
I remember trapped ions we use light to cool the atoms. So whether this cooling process is the same as the process to make them incoherent?
The cooling process, I think is a different process. I don't remember what that is now. Can you tell me what they do in? I know they trap particles with light, and I don't recall exactly how they do that.
I remember there are like four electrodes and two diagonals with RF fields, and the other two diagonals are grounds. And in this way, you can generate a harmonic potential, something like that, to trap the ions in it.
No, that is different. I think that will be different. You want to manipulate the quantum state of these ions, okay, after they've been trapped. Okay, you want to manipulate the quantum state of these trapped ions, and you use another source that is coherent to manipulate them. So if this is manipulated to precess at a certain rate, this is also manipulated to precess at a different rate or so. They might have a different initial conditions, and then when they evolve coherently with respect to each other. And all these quantum states will be in quantum coherent. I think that will be different from what you're talking about. I recall the use of light to trap ions in some conversation I had, but I forgot exactly what they did there now. Do you remember anything like that?
A little bit, but it has to do with tuning the frequency of the laser field and using Doppler shift. So if the atom was moving against the light, then it's going to absorb it, and it's going to it has equal chance to radiate in either direction, so it gets slowed down. So by doing this, you can establish a well.
That's right. That's right. I remember something like that.
Something like that.
There's Doppler shifting involved.
Yeah,
you shine light on the whole bunch of ions. These ions are moving randomly. Okay, they move randomly in all directions. Kinetic energy cause them to move randomly. But if you shine light in them in different directions, you tend to cause them to lose energy in the preferred direction and then start to collapse. And then they start to collapse and cool down. Okay, they start to lose energy to the light, and then they get trapped. Okay, there's one way to trap things. I also have seen other people describe on how to make ion traps using defects in semiconductor devices. If you use defects in semiconductor devices, then you can actually generate artificial atoms in semiconductor devices, okay, because you have holes, and then these holes can play like a nucleus, and then you have an artificial atom. You looking for something?
A door. trying to shut a valve off. Thank you.
Okay, so there are different ways of generating trapped ions. You can actually create artificial atoms rather than real atoms. I think there's a trend now, using artificial atoms to do quantum computing rather than real atoms. Artificial atoms can be engineered to different properties, whereas real atoms are harder to work with. Okay.
So you're using ion traps, but instead of using the traditional atoms, you use artificial.
I'm not truly clear about how they do that now, because if you look at some of the artificial atoms, maybe Ian did some literature research on those, you can get the artificial atoms to have different quantum states. And you might want to use only two of the levels. Two of the levels in this artificial atom to represent the zeros and ones, the qubits. And then you manipulate these artificial atoms to evolve with time. And then you can do quantum information, quantum manipulation with that. I think you also did some literature survey on some other kinds of artificial atoms, right?
That is more or less like for transistor using quantum
Right, right.
for this purpose.
Right. So there are different kinds of artificial atoms being studied at this point. One artificial atom, the ion.
We'll talk about this maybe Tuesday.
Okay. So like Ian did some literature research on Cooper pair boxes, and those have been used as artificial atoms as well, because they can be made very small and can be engineered to have different properties. Okay. So let me move on to a different topic in addition to quantum computing. Okay. I'd like to talk about quantum teleportation. Quantum teleportation. Okay. So if you have Alice and Bob again, okay, Alice and Bob. Okay, there's something I forgot to mention about BB84. Okay, BB84, how it is actually used in the real world application. I told you about the fact that in the algorithm BB84, you have Alice and Bob, one holding a vertical polarization, the other like a horizontal one, and then they switch to 45-degree modes. And then you randomly do the transmissions and receptions. And if Eve is dropped on them, they can detect Eve quite easily because the data will be corrupted. So if they do not detect an eavesdropper, then they would think that their quantum communication system is clean. Then they will send an encryption key to the quantum communication system. So Bob receives Alice's encryption key, and then they send a whole bunch of codes and information using a public channel. Okay, public channel like the ordinary channel. And then they will periodically test their quantum system to make sure that it's not corrupted. And if it's not corrupted, then they can send some key information over the quantum system. And then reuse a public channel to communicate again using an encryption key that they know to be a secret that nobody else knows about. Okay, so that is how this BB84 scheme has been implemented in real world, okay, for quantum communication. But quantum teleportation also involves Alice and Bob, okay? Alice and Bob, and let's talk about how Alice and Bob can send information to each other. Let's assume that Alice, okay? Alice has a photon that is in this linear superposition of two states. Okay? And this photon is available to Alice. And then Alice is available of having with her another photon. Okay? The photon is also in a 0 and 1 state, and she wants to figure out how she can send the information, the state of this photon, to Bob. Okay? This belongs to Alice, right? How can she do that? it seems that there is a scheme of doing that. What they do is that with the second photon, okay, the second photon belongs to one of the 4 Bell states. Remember, I went through these Bell states that we have, okay? There are 4 of them, and the other photon is entangled with a third photon. So there are 3 photons involved. Alice has this photon, and then she has another photon with her. That's entangled with the third photon. Photon 3. And she can send photon 3 to Bob. Okay? And Bob just had to know photon 3. And it turns out that he can figure out what state of the photon 1 is. Let's see how we can do that. Okay? So there are 3 photons at play at this point. And let's describe the state of the 3 photons to be in one that belongs to Alice, okay, the other one is an entangled pair, okay, and part of this Alice has, the third photon Bob has. Okay. And this is actually a Bell state. This is actually a Bell state, the psi minus 1 state, psi minus state. Okay, one of the Bell states. This photon 2 and 3 actually belongs to that. Okay, and then if I were to list out all the Bell states, they are actually given by this 5 plus. The 2 photon states that are in the Bell states are given by 1, 2, and then plus or minus 1, 1, 2. Okay, this is plus or minus. There's 2 of them over here, and then the psi states plus or minus are going to be 1 over root 2. 0, 1, 2, plus or minus 1, 0, 2. Okay, these are the 4 Bell states. It turns out that these 4 Bell states are orthogonal to each other. You can multiply them together and find the inner products. They are orthogonal to each other. We can do a very simple one. You can do, say, psi plus 1, 2 with psi minus 1, 2. Okay, and show that they are orthogonal to each other. And what we do then is to take the transpose of phi minus. Okay, we'll get something like, I guess 0, 2, and then 1, 0, minus 1, 2, and then 1, 1. Okay, and then multiply that with the other one, which is 0, 1, 0, 2, plus 1, 1, 1, 2. Okay, you multiply this out, the inner product with this, you get 1 and 1, right? This term multiply this term inner product if you want. And then this term multiply this term inner product will give you minus 1. Okay, the cross terms are orthogonal to each other. They are orthogonal to each other because 1 and 0s are always orthogonal to each other. Okay? So you can see that they are orthogonal to each other. If you go through all the exercises, you find that all these Bell states are orthogonal to each other. Okay? And there are 4 of them. So, I can expand this out into different ways of expressing this by multiplying them out. If I multiply them out, I get these 3 photon states to be equal to 1 over root 2 C0, 0, 0, 2, 1, 3 minus C0, 0, 1, 1, 2, 0, 3 plus C1, 1, 1, 0, 2, 1, 3 minus C1, 1, 1, 2, 0, 3. Okay, I can expand this out, I get 4 terms. Okay, I get 4 terms after I expand this out. And then now you can project this into the 4 Bell states. I can project this into the 4 Bell states, and then rewrite this as a linear superposition of Bell states. Since these are complete, okay, I can take the other 2 all these Bell states, and project the left 2 photons, the first 2 photons, into the Bell state of the first 2 photons. Okay, and I just project these states. Since these are all 2 photon states, then if I do the projection, I won't go into the detail. Okay, if I do the projection, I can rewrite this as being the linear superposition of Bell state for the 2 photon state times C0, 1, 3 minus C1, 0, 3. Okay, this is like doing a Fourier series expansion of some sort, and then I will have the second one being C minus C0, 1, 3 plus C1, 0, 3. Okay, and then you keep projecting and finding the other ones, psi plus 1, 2 C0, 0, 3 plus C1, 1, 3. Okay, and then the fourth one will be minus psi 1, 2 C0, 0, 3 plus C1, 1, 3. Okay, so essentially it's just like a Fourier series expansion. You have 4 complete in orthogonal states. You project the 2 photon states that are to the left into these 4 states, and these are the answers that you get. Okay, I hope I don't have to go through the derivation, but it's a simple projection problem. Do you want me to go through the derivation, or it's pretty much understood how it should be done? You project and find the coefficient, project and find the coefficients. You take these 2 photon states, you find the coefficient, okay, for all the different things. You can find C0s, and then you do the same thing to the other ones, and you find all this 4 projections. So then the question is, how do I teleport this information of the first photon to the third photon? Okay, photon 3 is shown to be something that is outside the Bell states now. Okay, photon 3 are given to be this after this projection. So the diagram goes something like that. Okay, I have a Bell state measurement machine, okay, that if I have input photon coming in, and this photon is in one of these 4 states, 4 Bell states, okay, I don't know which Bell state it is in, okay. The Bell state photon machine is going to measure this photon and light up one of these lights. Okay, it is going to tell Alice that the first 2 photons is either in this state that state, one of these Bell states. Okay, or one of these Bell states. So it could be this thing will light up or that thing will light up. So one of these will light up. Okay, depending on what Bell state the machine finds it to be in. Say it is a psi minus state that the machine finds it to be in, then that light will light up. Okay, it's one of these four Bell states. They are orthogonal to each other. So then what happens is that you actually need another photon coming into this Bell state machine to create all this. You actually need a source that can create photon 2 and photon 3 to be in the entangled state. Photon 2 and photon 3 are entangled. Okay, 2 and 3 are entangled. So you have this photon source that generates photon 2 propagating in this direction, and photon 3 goes to Bob. Okay, photon 2 goes to Alice, photon 3 goes to Bob. Okay, Bob has the photon 3 machine, and Bob has this photon. Okay, Bob can send it through a decision-making machine called U, plus that he is going to get this information classically from Alice, from a classical channel. Okay, Alice is going to tell him which light lights up. Okay, which light lights up. If this light lights up, say, then Alice will tell Bob that it is this state that I'm in. Photon. Okay, the 3 photons are going to be in that state. The photon 1 and 2, okay, is going to give me something that I have in this state. And then Bob is going to look at photon 3. Photon 3 must be in this state. Okay. If Alice tells Bob that photon 1 and 2 are in this state, then photon 3 must be in this state. Okay? Do you get it? So if photon 3 is in that state, in order to find C0 and C1, it's quite easy for Bob to figure out what C0 and C1 are, because he can go through a machine that decides that if it's psi 3, then you just have to figure out that the photon 3 is in the linear superposition of this state, and he can figure out what C0 and C1 are by measuring the state of psi 3, photon 3. Okay? You can figure out what C0 and C1 is. And if Alice decides that there's some other states over here, for instance, okay, that photon 1 and photon 2 is in this state, then Bob knows that the photon that he has must be in this state. You can do a measurement to figure out what C0 and C1 are. Okay, so that information is actually going to Bob. So you, in a sense, have transferred the information of a photon state from Alice to Bob. This is called the quantum teleportation. Is this understood, or is this clear?
I'm wondering whether Bob needs to figure out what C0 and C1 is. Is it necessary, or is it okay for him just to know just which one of the 4 states is in, instead of knowing exactly C0 and C1?
If he wants to know exactly what quantum state Alice photon is, he has to know what C0 and C1 are within a phase factor. Okay, so within a phase factor, he has to know what C0 and C1. So he can perform a measurement, a kind of a measurement on his photon, and figure out what C0 and C1 are. Okay, he can design measurements to figure out what the 2 states, that maybe it can be upspin or downspin, or in the case of photon, it could be vertical and horizontal polarized. And then he can figure out what the 2 states are, or right-hand circularly polarized, or left-hand circularly polarized. And he can figure out what those C0 and C1 are to within an arbitrary phase factor. Okay? And then he can figure out the state of the photon that Alice has. Okay. So, so then I like to talk about the Bell theorem next. If you don't have any question on this, the Bell theorem. Yes. Oh, you have a question? Yes.
I want to ask, is that can we just like copy the quantum state of the first?
No, it's not. Actually, you have to destroy the quantum state. When you do a measurement, when you do a measurement, you have to destroy the quantum state of this photon in order to decide which Bell state you're in. So there's no violation of the no cloning theorem because the photon 1 has been destroyed when you get this information. And then, but the information is transported, teleported to photon 3. Okay? So that is the idea behind this quantum teleportation. Okay, any other questions?
I'm curious, what's the advantage of this teleportation method compared to classical? You still need to share the classic information, but about to know what those full Bell states the light is on from Alice. So
No,
it's still classical.
she has to just send one of the 4 numbers. Okay? Whereas if she has to send these numbers C0 and C1, there are umpteen possibilities, right? And there are a lot more numbers to describe. C0 and C1. Okay? So in a sense, it's a lot easier to send this information than to send the entire state of the photon over to Bob. And in this manner, she can send the entire state of the photon to Bob. Okay? So if not, I'd like to talk about Bell's theorem, if you don't have any more questions.